In the last video, we discussed how to find the volume of solids generated by revolving a region around an axis. I'm going to do the same thing in this video, but let's think back to that last video. So let's take a basic shape. If I were to rotate this around the x-axis, that would be a very easy shape to use. We talked about washers and discs in the previous videos. It'd be very easy to use really just a disc. If we're taking that cut that is perpendicular to the axis we were revolving around. So here we're revolving around the x-axis. Very, very easy to find that just with a disc, or even if we had some outer inner function, it'd be very easy to use a washer. But one of the last problems that we did in that last video, we revolved it around the y-axis. So what we saw when we revolved around the y-axis, rather than having this integral set up as some area on x, of course we need our pi and we need our squared dx, where these are in terms of x's. Well, if we're revolving around the y-axis, then everything has to be in terms of the y. So if I'm revolving this way, well then our integral goes from c to d of pi area in terms of y squared dy. And so in the last video, that wasn't terribly challenging to do. We could solve the equation for x, and we got to our volume. But as I alluded to in that video, it's not always real easy to solve for just the opposite variable. We can think of a number of equations. If we had something like y equals x squared plus x minus 5, that's much easier to view in terms of y rather than trying to solve it for x. So if I have to take that equation and then revolve it around the y-axis, well then somehow I have to write everything in terms of y. That's just not going to be feasible. That's not going to be easily done. So we're going to think of a different way to approach this problem over here on the right when we're rotating about that y-axis instead of the x. So we can still see that there are outer and inner diameters. We can see the same picture. If we were to think about what this would look like, we'd have the kind of equivalent picture over here, and it would be this area here, kind of a ring in a way, but or almost a mountain range with a valley in the middle, or a low point in the middle. But what we want to think about is, if we can't easily write that in terms of x is equal to, what could I do? Well, whenever we were using our washers, we were always taking cuts. We were always taking these slices, and that seemed to work pretty well for us. And we always did it perpendicular to the axis that we were revolving around. We're going to do, let's try making a cut parallel to the axis of rotation. So both of these are vertical cuts, but here we're rotating around the x-axis, here we're rotating around the y-axis. So the key is, when we're using washers, we are slicing perpendicular to the axis of rotation. If we're going to use shells, we're going to make slices, or we're going to slice parallel to the axis of rotation. So let's think about what that does for us. So again, this little red line in here, that shows my little sliver. I'm making that cut, just cutting through a bit of this thing. I'm going to think of it, could think of it like a cake in a way, or a bundt cake where that center has been removed. So we're taking a slice of that cake. And so let's blow that up for a second. Let's think about what that shell looks like. And so if we're taking that cut, we're doing so around the shape. We're taking that cut throughout the shape. And so what that's going to give us, we have this cut the whole way around. That's going to be a kind of a cylinder, a hollow cylinder. I'll try my best to draw this. That's a decent, not great. But think of like a toilet paper roll. Right, if we've taken this cut, but that cake is spanning the whole way around, it's giving us this toilet paper, this paper towel roll, where we have just a small thickness here, however wide that cut is. And then obviously there's a height, and there is some sort of length associated with the exterior of this shape. So if we take this paper towel then, this paper towel roll, and unroll it, we have height and we have the length. And then the thickness, this piece right here, that would be how far we have cut. That would be how far we've come on the x. That would be our dx. And so now that we have this shape, right, how do we find the volume of this shape, or the area of this shape? The area would just be length times the height. But then, of course, once we have a volume, we're going to have the length times the height times the width, or the dx. We've already named the dx. Now, what is this L? How do we find this L? The h obviously is simply the y-coordinate, or we can think of h as the function value, in this case in terms of f of x. The L is the whole distance around the exterior. That would be this exterior distance here, which is a circumference. L is circumference. Squeeze that in. And so how do we find circumference? Well, circumference is equal to 2 pi times the radius. And then the radius is equal to, in this case, the x, as long as we are centered around the axis of rotation. So like we saw in the last video, we're going to see some cases where our center or what we're rotating around is not just the x or the y axis. So we will get to some examples like this as well. So let's come down here and formally define this shell formula. The volume of the solid generated by revolving the region around the x-axis in the graph of a continuous function y equals f of x greater than or equal to 0, where our x is greater than a, which is also greater than the L, which is going to be the vertical line we're rotating about, and then x is less than b, so it's in that interval, then the volume is equal to the interval a to b, the integral a to b, 2 pi times the shell radius times the shell height dx, just what we defined just a second ago. Now, there were some stipulations here. We said that the function has to be greater than 0, positive. Now, can we correct for it if it is not greater than 0? Absolutely. We know how to work with functions. We know how to work with integrals to where we can make things positive if we need to. And then the other stipulation was that our a was greater than the L. Well, what if we're rotating about something that is actually greater than the a? Well, again, we can make those adjustments. We will understand how to make those adjustments. So let's start with an example. We're going to start with a more simple one, and we'll build up to a more challenging problem. So let us find the volume given a region bounded by y equals x squared, the x-axis, and x is equal to 3, that is revolved around the y-axis. So just as we've done time and time again in this section, I'm going to start with a picture. So x squared. There's my curve. X is equal to 3. And then the x-axis. So we're looking at this area that is being revolved around the y-axis, and it's giving us similar pictures to the last one, a little different spot, but kind of that idea of kind of a bowl. It would look very much like a bowl with these pointed sides. So let's start dissecting what all of our pieces are. Remember, in our formula we said we need the shell radius and the shell height. So let's start with the shell radius. We are rotating around the y-axis, so when we're thinking about our slices, I'm going to physically draw those slices on there. And it can be simple, it can just be that vertical line. But here in red is my vertical slice, my slice parallel to the axis of rotation. If we think about what the radius is, this distance right here, that is simply equal to the x. So in this case, shell radius, very easy, is just x. The shell height, well, that is equal to the function value. So in this case, it's x squared. And then the thickness of the shell, how thick is this red line right here going side to side? Well, the thickness is the dx. so now we can find our volume. Everything is in terms of x. Notice if we were to have used washers, washers would have been a more challenging problem because we would have had to have thought about the slices going the opposite way, meaning the slices in blue here. We would have had an outer radius, the 3. We would have had an inner radius, the function. We would have had to have solved that function in terms of x. Now that's not real challenging on this one. It would just be the square root of y. But notice it becomes a more complex problem because we'd have those two elements to it rather than just kind of thinking this as one slice. So let's go ahead and evaluate our integral. Let's see if I can get my pen to switch back over to black. Not that it really matters. So we're going to integrate from, well, our lower end point was 0. Our upper was 3 because we're thinking about this in terms of the x. We have our 2 pi because it is a circumference. The radius we said was x, and then the height was x squared dx. So I can do a little simplification here first. 2 pi, I'm going to integrate from 0 to 3 of x cubed dx. And so we get 2 pi, and then the antiderivative of x cubed is 1 over 4 x to the 4th. We're going to evaluate that between 0 and 3. So I'm going to plug in my 3 first, 1/4, 3 to the 4th, minus 1/4, 0 to the 4th, which is just 0. And so 3 to the 4th is 81. 2 goes into 4 twice, and we still have our pi there. So 81/2 pi units cubed, because it is a volume. So that's a relatively simple one because we just revolved around the y-axis. Let's take another example. Let's find the volume of the solid generated. Solid. By revolving the region enclosed by x is equal to y squared, x is equal to 0, y is equal to 2, and y is equal to 5 about the x-axis. So I never gave you a formula for revolving around the x-axis, but we should be able to do it without a whole lot of trouble. Let's draw out the picture and we'll think about it. It's going to be the same concepts, just revolving around the x-axis now. So x is equal to y squared. Well, that's going to look like our square root function because it is just a square root function, but it'd be going both up and down. We are going to take the y is equal to 2, which would be up here, and y is equal to 5, which would be even higher. I'm not going to draw this really to scale. Let me even move that 2 down a little bit just so I have a clear idea what's going on. So 2 and 5. There we go. And so we're taking this region, also bound by x is equal to 0, which gives us the third side. So I can kind of ignore that bottom half right now. I'm taking that region, I'm revolving that around the x-axis. And so if I was to use washers, which I could do, I would need to figure out what this is in terms of y, and we could do that, and we'd have an outer washer, we'd have an inner washer, and we'd take those two radii, square them, and subtract them. That would work, that would be fine. But does this become an easier problem with shells? Very possibly. So let's see what's going on. So if we want to use our shells, we have to take our slices parallel to the axis that we are rotating about. So that means we are taking now slices that are parallel to the x-axis running left and right. Now if we think about the thickness is equal to dy. Notice I started with that right away on the last one too. I thought about that thickness because once I can determine that, that's going to tell me if I have the dx or the dy. Same thing for the shells. Think about what your slice looks like. Think about that dx versus dy, and then we know what we need to have all the variables in terms of. Very clearly here we need to have everything in terms of y squared. So the next thing I need to do is I need to think about my radius, my shell radius. That shell radius is the distance from 0 up to that line, which is simply going to be the y value. And then I also need to think about my height. And the height now is what's running left and right. So the height would be from this point to this point. And so what's giving me that? Well, the equation of my x. My x value is giving me the height, and x is equal to y squared. So I need to use the y squared because I need to have it in terms of the same variable. And then obviously the limits, we are going from 2 to 5. So now let's set up our volume problem. We're integrating from 2 to 5, 2 pi. Our shell radius was y. Our shell height was y squared. Then our equation dy. Notice it's looking very, very similar to how we did the last example. Just now we have y's in it instead of x's. So I can pull out my 2x, going from 2 to 5, y cubed dy. So I'd have 2 pi y to the 4th over 4 when I find my antiderivative. I'm evaluating between 2 and 5. So we'd have 2 pi 5 to the 4th over 4 minus 2 to the 4th over 4. And now we just need to simplify. If we take 5 to the 4th, we get 625, I believe. Just double checking that. Yeah, 625. 625. 2 to the 4th is 16 over 4. And so when we subtract those, 2 pi, what is that, 609 over 4. We can, of course, divide 2 into 4 twice, and so we get 609 pi over 2. And so there is an example where we have rotated around the x-axis. Is the same process, but just like we saw with our washers, we had to change up what variable we're thinking of in terms of. So physically draw that cut, that slice into your picture, and think about the thickness of that slice. It doesn't matter if you're using washers or if you're using shells. Whatever the thickness of that slice is, if it's dx, everything's in terms of x. If it's dy, everything's in terms of y. Let's do one last example. Find the volume of solid generated by revolving the region bounded by y equals x squared, y equals 0, x equals 1, and x equals 2 about the line x is equal to 3. Don't know why there I wanted x is equal to 3. So let's start with our picture. X squared, we know what that looks like. We are looking between 1 and 2. Put 1 here. 1 and 2. So we have this region right here. Of course, the curve is in my upper half, and then y is equal to 0 is my lower. So we have this region right here, this shaded area. And we're revolving it actually around the line x is equal to 3. Excuse me, x is equal to 3. So we're revolving around this dotted line right here, which means we're going to have the other half over here. That's not a great picture, but gives us the idea. And we're doing these revolutions right here. We're going to have this going this way. So let's think about what we want to do. If I'm revolving around y, not the y-axis per se, but something that is parallel to the y-axis, so this vertical axis. Therefore, if I were to use the washer method, I would have to solve this thing in terms of x again. I would have to look at the outer washer and the inner washer. I'm just going to avoid that entirely by using my shells. So when I take my slice, I'm going to take it parallel. Tablet's not changing colors again, but I'm taking this slice right here, There we go. Taking this slice right here, parallel to the axis that we were rotating about, parallel to that, y is equal to 3. So if I think about that parallel slice, that is a dx, which is why I'm using my shells, because everything is already in terms of x. I'd rather use that. So our thickness is the dx. I need to think about my radius. I need to think about my height. Now actually the height's the easy element here. The height, we're clearly going from 0 up to the curve, so the height is equal to the x squared. The radius is going to take a little bit more thought though, because we're not rotating about that line y is equal to 0. Remember, this is where we said that that formula that we're given kind of falls short. It says that that line needs to be to the left of the integration bounds, and that's not what we're doing here. So we need to think about this radius. Well, the radius is from whatever x value we are at up to the 3, which means to find that distance there, we need to take 3 and subtract that x value. Same way we were doing with washers. We did the same calculation. We said if we wanted this distance from here to here, we simply subtract. We take the larger number, we subtract the smaller number. 3 minus, and this smaller number is the unknown x, wherever it happens to be landing. And so now we have all the information we need to integrate. We are integrating from 1 to 2. Those were the limits that the problem gave us. Our formula, 2 pi times the radius. The radius we found to be 3 minus x. And then the height was the x squared dx. So I'll start with a little simplification. Pull out our 2 pi. I'll be integrating from 1 to 2. We go ahead and distribute that x squared. So we have 3x squared minus x cubed dx. And now we can find our antiderivatives, x cubed minus x to the 4th over 4. We're integrating from 1 to 2. That's a pi, not an x. Let me clean that up right here. That's a 2 pi. And now I'm going to plug in. So 2 pi, 2 cubed minus 2 to the 4th over 4 minus, then we'll have 1 cubed minus 1 to the 4th over 4. So we'll have our 2 pi. 2 to the 3rd is 8 minus 2 to the 4th is 16, but divided by 4 is going to be 4, minus, we'll have a 1 minus a quarter. So 2 pi, that'll be 4 minus 3/4. So 4 is 16/4 minus 3/4 would be 13/4. And so we get 26 pi over 4, which we can simplify to 13 pi over 2. And that is our answer. So we just really have to think about what we're doing. Don't concentrate on what the formula is per se. Don't always think, oh, my radius is always x, my height is always the function value. No, we have to think about each one uniquely. And we always want to be kind of on the lookout, is there an easier way to do it? Because we're concentrating on shells in this video, we're concentrating on washers in the last, but what if I don't tell you? What if I just say, hey, here's a solid, find its volume, use whatever you want? Well, generally what I'm thinking about is what is the equation defined in terms of? This was defined in terms of x. So I'd really like to take those vertical slices. I'd like to have those dx's, made that even messier, but dx's here, because that is what everything is in terms of. And so if I'm going to take dx's, I'm taking vertical slices, which means I'm parallel to the axis of rotation. That gives me a shell. Versus if I had instead had an equation, something like x is equal to the square root of y. Well, now I have something that it's already in terms of y. So maybe I'd like to take those y slices. Well, if I'm taking y slices, that means I'm dealing with a perpendicular to the rotation. It means I'm going to have to take my washers and use that. So we do want to practice with both methods. We should be able to go from one to the other in a lot of cases, but not all. Because again, what if I give you that function that y is equal to 1 over x plus x cubed minus 3x squared? I just don't want to have to ever write that in terms of x. I never want to have to solve that for x. So I'm definitely going to use dx's. And that means I'm going to have to parameterize around that for whether I'm using a shell or a washer. So think about what the picture looks like. Think about which way you're slicing. Think, am I parallel or perpendicular to that axis of rotation?